the space and time session for Euroviz this year. Space and time session for Euroviz this year. Okay, technical fail. Sorry about that. Again, welcome to the space and time session. Our first paper is going to be titled Momento, Localized Time Warping for Spatiotemporal Selection. It will be presented by Veronika Schulte-Sova, and she will be here to answer questions with also Noeska Schmidt, and the other authors on that paper are Sergej Stapel, Renata Gruner, and Stefan Bruckner. So Veronika, go ahead. Or Veronika's recording, please go ahead.
Dear ladies and gentlemen, thank you so much for coming to listen to my remote presentation of the paper Momento, Localized Time Warping for Spatiotemporal Selection. My name is Veronika and I will be presenting this paper. However, this was a collaboration of myself with Noeska Schmidt, Sergej Stapel, Renate Gruner and Stefan Bruckner. The main motivation for our work are the challenges associated with visualization and analysis of spatial temporal data. That means data with an spatial and a temporal dimension, such as, for example, surveillance videos, that is 2D plus time, or streamed 3D medical data. That would be 3D plus time or 4D data. The problems associated with different types of data are many. For example, imagine a little bit boring surveillance video where the user is already fatigued and his or her reaction time is slow. An important occurrence happens and he needs to react quickly, but his reaction time is too slow. Another problem is that pausing the stream globally is not really an option because the user or analyst can miss very important information, which is especially a problem in the medical domain. And what we want and what we are missing is a holistic spatial temporal interaction technique that prevents exactly this information loss. So what has been done in the previous research? Some works have been focusing on creating one single representation of the stream or playback. For example, identifying the motion and illustrating it with glyphs, or integrating and projecting the temporal dimension into a single image. However, lots of information gets lost if you imagine that you project an entire stream into one single image. Therefore, this can be considered insufficient for certain tasks. Then there are dynamic representations that capture more information. Here, the closest work to our approach is the paper of Le Musique and others, where they present the so-called timelines and temporal zooming, where they can predefine zoom into trajectory of a certain object. And this is different to our technique, where we present a method of directly influencing the playback or visualization of the stream using user input. All in all, we have noticed that the interactive techniques available, they sort of neglect the whole 4D aspect of the data. There is interaction that there is either spatial or temporal, but we were kind of lacking one holistic point of view at spatial temporal interaction. Our approach makes the contribution of an easy-to-use interaction tool to interact with the visualization, and that is spatial temporally. What does the user gain? He can warp at the time locally without losing the context. At the same time, have more time to observe details in the selected region and does not need to pause or rewind or otherwise alter the stream or playback. We propose a pipeline of a new holistic spatial temporal interaction method. This can be viewed as 3 building stones of a pipeline, and if you choose to adapt our method, you are free to replace or adapt to your liking some of the building stones while keeping the concept. So the first is the specification of the temporal warping behavior, or so-called temporal warping function. Second, the technique of specification of the spatial temporal region. And finally, the visualization of the whole time warping process and communicating it to the user. We begin at looking at the first building block of the pipeline, the design of the time warping behavior with the time warping function. In short words, it is the function that defines the relationship between the global time, t, which is here on the x-axis, and t prime, which is the local time in the selection. If we have a diagonal, means that we have a linear dependency or identity mapping, and then there is no deviation. But what can we do if we want to define a deviation? We have so-called design space, or a window, with a size of a big W, which starts at t0 and ends at t0 plus W. And in the beginning and in the end, it has to return to the global time. So if we start the interaction, the time in the selection can deviate. It can go, for example, a little bit backwards, pause, and then catch up, as it is in the leftmost visualization, design space A. And then in design space B, we have a little bit of slowdown and then catching up. And in design space C, we have a jumping back few frames and then the same speed of playback for a while until we catch up. The second building block of the pipeline is the selection of the spatial regions itself. Here we use a brushing technique, and we have a variety of brushes to choose from. First, it's a so-called paintbrush or additive circular brush. And it's a simple rectangular brush, simple circular brush, and the lasso. Here the user can choose whatever he likes or prefers. And it's also worthwhile to note that the interaction starting point, T0, is defined when the user clicks and starts to select with the brush. The third and the final building block of the pipeline is visualization. Here we already see that there are many different possibilities to do this. However, we have chosen to visualize and communicate both what happens in the global time and in the spatial selection. So therefore, we have extracted salient features from the global time as edges and composited it with the time warped image in the selection. More details you can read about the paper and also about the further experiments. While watching the videos on the previous slides, you might have noticed two widgets that haven't been explained yet. The first is called Time Warping Curve widget that serves to illustrate the design of the time warping function. Here we have the black line, which denotes the identity time curve, and the blue line that denotes, that visualizes the design of the time warping function. So in this case, we have a quick return by 9 frames, and then very slow progress of 2 frames spread over 8 frames, while in the duration of the last frame, we catch up with the global timeline. The 2 dots, the black dot and the blue dot, denote the current location on the global time and the local time in the selection. The second widget is the warpometer widget that denotes the distance in time, the temporal distance between the black and the blue dot. As you can see from the design, that this distance is constantly changing as the time progresses, so it's important to actually communicate it. T0 is again at the beginning of the interaction. And here we can watch this on a video. In the top left corner, we have the time warping curve widget that denotes delay. And here we have the warpometer widget that denotes the temporal offset. We have demonstrated our interaction technique on a variety of use cases. First, we have two video stream examples that are easier to understand. In the first one, we have a very long surveillance video where a single interesting event is occurring, and that is a delivery of some kind of a package. So here, the challenge is that during the long surveillance, the user might be fatigued and the reaction time might be slower. So by a single click and quick brushing, he is able to revert the playback a little bit, while he can still keep track what is happening in the global time. In the second video stream use case, we are synchronizing ballet dancers performing Kanon choreography. However, the main aim of this work is to apply this interaction technique to 3D data plus time. Here we have an example from cellular biology, a cell division, that is data coming from confocal microscopy, and functional MRI. Let's have a closer look at the fMRI data use case. As a data set, we had an Nuska's brain consisting of the T1, the structural anatomy data set, and functional data series consisting of 100 3D scans. We had the so-called block design study where she was first tapping with her left hand, then there was a resting state, and then tapping on the right hand. And we would like to synchronize the tapping. So here is a video of the demonstration. Finger tapping on the left, finger tapping on the right. Then there is a resting state. And using a delay design of our time warp function, we would like to synchronize these events in the brain so that they occur at the same time and we can compare. Now we have seen our interactive time warping method in action. To sum it up, it is a holistic approach to manipulate the visualization and playback or streaming of temporal data sets. But we are not done yet. There is still future work to be done. We envision to explore the potential and use it on interactive 4D visualization of more interesting fMRI datasets. And maybe we will be able to synchronize entire networks in the brain and multiple regions. Thank you for your attention.
All right, terrific. Thank you, Veronica. So at this point, we will open things up for questions. And I guess I will start things off with a question. I always wonder if you were to run a user study with this, and what would be the base condition? In other words, what's the current best state of the art? And how would you compare to that?
So it really depends on the task you want to do. So for example, for editing videos, you could perhaps design a task using state-of-the-art software for editing videos. And you could maybe give the user a task to do this, like measure the time or see if he is able to catch up details while he's streaming some videos, like yes or no questions, perhaps. But then another interesting thing would be to do a study with medical personnel, for example, analyzing fMRI. And this is actually something that we as the team of the co-authors were thinking to move on, the future work to investigate this avenue further on.
And what do you think the outcome would be? Would people be faster, or would they like it more, or would it cause them to cure cancer, or what's the level of comparison you would imagine?
So maybe, and we agreed with Nuska that she will answer the questions related to fMRI. So I think she can give she can say something interesting.
I can definitely say that we're aiming to cure cancer. That's one of our main goals here. But seriously though, in fMRI analysis, very often what people are doing is they're only looking at a static summary of the activity over time. So this in itself, already playing the fMRI activity as an animation, is sort of an innovation that is new to the field. And it may open the door to future neuroscience discoveries. But at this time, this is something we're still evaluating.
Okay, terrific. One other question from the YouTube channel is whether you considered applying similar ideas to non-video data, for example, spatial time series.
How this is like the architecture, how this is implemented or programmed, is that we actually have access to the full data sets, not just the images. So it can be really anything from the video data to streamed 3D data sets. And if you think one of the building stones was how to actually put this data together. So instead of just combining images, you can really go deeper and combine actually, change the rendering methods based on the data in full 3D. So it opens up for many possibilities, and the current hardware actually allows for it.
If I may add to that, also the use cases in the paper currently are based on 4D volumetric data. So the cell biology is a 4-dimensional scan, and so is the fMRI scan.
But yeah, it could be also, for example, simulation data in the future. Like one potential application that we were thinking about.
All right, terrific. Thank you both for the questions and answer session. Thanks for the questions from the audience. Please thank our speakers again in the YouTube channel, and through the miracles of remote attendance, I can keep talking even while you put your quiet clapping into the channel. So our second speaker today is Alireza Amiragdam, and he will be presenting Localize, locally adaptive line simplification for GPU-based geographic vector data visualization. His co-authors are Alexandra Deal and Renato Pajarola. So Alireza, go for it.
Welcome to this presentation. I'm Alireza Amiragdam from the Visualization and Multimedia Lab of University of Zurich. In this video, I will present our locally adaptive line simplification algorithm called Localize, which is mainly designed for visualizing geographic vector line data, but its application is not limited to this field. Vector line data is an abundant type of data in geographic datasets. The level of detail is usually managed by creating different versions of the dataset generalized at different levels. The shortcoming of this approach is that different levels of detail cannot be used side by side in one scene. In a 3D visualization, this shortcoming becomes critical because in many viewing angles, different levels of detail are required for different parts of the scene, depending on the distance to the camera. Otherwise, either the close parts will be too low in detail or the far parts will be too cluttered. Additionally, a large unnecessary data should be handled. To tackle this challenge, we have developed Localize. Localize simplifies lines non-uniformly, is based on a pixel-precise visualization technique for large vector line datasets, takes advantage of the GPU parallel computing power to run in real time, prevents unwanted intersections, and dynamically changes the thickness of the lines to reduce the clutter. I will explain each of these features starting with non-uniform line simplification. Our algorithm is based on Douglas-Poiker line simplification. For each line, we start with the most simplified version of the line. Then we add the point with the largest distance to the baseline. This distance is denoted as error. This point divides the line into two parts. For each part, we apply the same procedure, and in the end, we have a binary tree with nodes that represent points and their corresponding errors. After saturating the errors hierarchically, such that no node has a lower error than any of its descendants, we can simplify the line by pruning this tree while traversing it based on any given error threshold. Like this example, the error threshold can be a function of distance to the camera. Next, I will explain our pixel-precise 3D visualization of large line datasets. Recently, different vector rendering is introduced for visualizing large number of lines in 3D, which takes advantage of the power of GPU. Localize uses the same concept. The color of each pixel is determined independently by comparing the distance of the pixel to the lines and the thickness of the lines. To limit the number of comparisons, an optimized search hierarchy is used composed of one grid and one quad tree in each cell of the grid. As a result, Localize provides a pixel-precise rendering of a large number of lines at any zoom level without using proxy data structures. Now I explain how we parallelized our algorithm to run efficiently on the GPU. Direct access to the vector data on GPU is a benefit. However, it is not possible to traverse trees redundantly for each pixel in real time. In order to make simplification possible in real time, we first create a set of all possible line segments that can emerge during the refinement process. The visibility of each of these line segments depends on 2 points. For example, this purple line segment will first appear when this green point is included. We call it generator, and will disappear as soon as this red point is included. We call it splitter. Storing all possible line segments with the generators and splitters as their attributes allows us to determine the visibility of line segments individually, which fits the parallel processing nature of GPUs. In order to have a valid line, no point should be included in the line when even one of its ancestors is excluded. In this example, the red point should not be included when the green point is excluded, or the green point must be included when the red point is included. This can happen when the error threshold is a function of distance to the camera and the ancestor is located farther from the camera. To solve this, we conservatively assume a lower distance to camera when validating the green point such that none of the points in the subtree can be possibly closer to the camera. The amount of this decrease is the maximum of distances between the green point and the points of the subtree and is denoted as Dmax. We calculate Dmax beforehand and store it with each point. For the same reason mentioned earlier, we also saturate Dmax. Lines can now be simplified non-uniformly based on an error function on GPU. In this example, we are using a lens that has a low error threshold inside and a large error threshold outside, plus high level of details inside and low level of details outside. The details are being added and removed to the line as the lens approaches and hovers over the line. In this example, the underlying set of all possible lines are also shown for demonstration purpose. Another challenge is to prevent intersections between lines when they are simplified. To solve this, we find all possible intersections. An intersection can happen when a point, such as B, is located in the triangle that excluding another point, such as A, creates. In this situation, excluding A before B results in an intersection. To prevent such intersections, we find all such dependencies and involve them in the saturation process of error and Dmax. As a result, no dependent point will be excluded before its dependees and no unwanted intersections will appear. These two examples show the unwanted intersections that can happen on the left and how Localize prevents them on the right. The last feature I explain is dynamic line thickness. Localize can dynamically change the thickness of the lines using a given function. This can be useful in wider viewing angles to keep the important types of lines visible while the others fade into the background. In summary, we get the lines as an input, create binary trees using the Douglas-Poiker algorithm, calculate error and Dmax values, find the intersection dependencies between lines, saturate error and Dmax values within trees and between intersection dependencies, and finally create a list of attributed points. At the same time, we create all possible line segments, find their generators and splitters, and create a list of attributed line segments. Then this data is loaded to GPU and rendered in the deferred vector map part of Localize. During the rendering, simplification happens on the GPU and this data is not required to be updated. Now let's watch Localize in action. In this test, we are visualizing the whole street data of Switzerland with 6.9 million line segments over a static train with all features of Localize active. The performance ranges from 6 to 75 frames per second in this setup, which is indicated at the bottom at several points as we go on. Localize increases the thickness of the important types of lines when zoomed out, so only the important lines are visible. As we zoom in, other lines become visible gradually until they reach their actual thickness. By default, the error threshold is a function of the distance to the camera. Instead of bounding the error threshold to the distance from the camera, we can adjust the error metric manually, which causes all the lines to be simplified uniformly at the same time. We can also use a refinement lens. The error threshold inside the lens is low, which causes all the lines inside to be at their highest level of detail. The error threshold outside of the lens is high, so the lines outside are simplified as much as possible. We can see that the details of the lines adapt to the movement of the lens immediately. Since we use the deferred vector map rendering technique, the lines are always pixel precise no matter how much zoom we apply. If we visualize the underlying quad trees, we can see the size of their nodes and how the line segments are distributed. The brighter nodes contain more line segments, and for the pixels inside these nodes, the GPU shaders have to do more distance to line comparisons to determine the color. This is the main reason why the performance is different at different zoom levels. We successfully implemented a real-time non-uniform simplification for vector lines in 3D by performing the operations directly on the attributed vector lines without using proxy data structures. The take-home message is that we can perform computationally intensive operations on vector data at render time on GPUs, which creates opportunities to increase the fidelity, flexibility, and responsiveness of the visualizations. Thank you very much for your attention.
All right. Thank you very much for your presentation, and folks, feel free to jump in and comment in the chat. There are a few questions. Michelle Kremer asks, what kind of visualization framework do you use? Have you considered web-based visualization with cesium, for example, and what data formats you're using for geospatial data?
Thank you first. And we implemented this currently in our own 3D rendering engine. But from the beginning, we tried to use the advanced features of graphics cards or APIs at the minimum level, so that later we can extend this algorithm to more various platforms. So in theory, yes, it's possible to extend it to web or other platforms, since we use the most basic features, and yeah, we can do that in future. It's a very good extension.
Great. I also wondered if you had any thoughts about how this might compare to terrain mapping, which has a similar kind of problem of retiling the surface as opposed to lines on the surface.
So in terrain, you're dealing with meshes, but like the concept is somehow the same. Maybe we can extend this concept to 3D meshes also. So they're like the idea usually in terrain rendering is to load the detail needed like at the time. Like as time goes on or the camera moves, so we load more data, and then we adjust the 3D mesh according to the new data. But here we try to load some attributed data to the GPU and use them only to simplify the data. So maybe we can extend this to also to 3D or terrain rendering also. But yeah, the concept is a bit different.
Interesting. And one last question I had was whether there are, I think you mostly set your error threshold to achieve a frame rate, or actually mostly to achieve a frame rate, I think. I'm wondering if there's a perceptual threshold that's appropriate in some way rather than a sort of a geometric one. You're sort of using that as a proxy for what's necessary for either achieving a frame rate or achieving a visual appearance, but I don't know what the right value is. I wonder if you have any thoughts on that.
Yeah, sure. We can adjust the error threshold exactly at the size of the pixel. So we can, since we are rendering online and doing the simplification online also, we can just know at each pixel how much detail can we show and adjust that error threshold to that amount of detail, so that, for example, when we zoom out or we zoom in, the user or the viewer cannot detect any changes in the lines, although the lines are getting simplified or refined on the fly. But it's not visible because that amount of difference on the pixels are very hard to detect. Yes.
Yes, that would certainly be a perceptual threshold. I was sort of wondering if there might be a less strong one, but I think what you're suggesting is a good solution if you can achieve the frame rates you want. Sure. So let's thank our speaker again and our co-authors. And while we're doing that, we'll move on to our next paper. This is going to be presented by David Sappho. His paper title is Data Comets, Designing a Visualization Tool for Analyzing Autonomous Aerial Vehicle Logs with Grounded Elevation. And his co-authors are Aristotelis Leventidis, Twinkle Jane, Michelle Borkin, and Cody Dunn. So let's go to the video.
This is Data Comments, designing a visualization tool for analyzing autonomous aerial vehicle logs with grounded evaluation. I'm David Sappho, and I hope you enjoy. Technology behind today's unmanned air vehicles is nothing short of amazing. What we more commonly refer to as drones have gone from massive, remote-controlled airplanes to being available in many designs, sizes, costs, and levels of autonomous capabilities. Like this one. For as little as $30 US, you can purchase a toy drone that is easy to fly, very small, can record video, and can even be programmed to fly autonomously or follow a target. It is undeniable that the use of drones is beginning to expand to many domains. Take for instance NASA, who've announced Project Dragonfly, which plans to send a quadricopter-like drone to explore the surface of the Jupiter moon Titan. Here on Earth, Zipline is a startup using drones to deliver critical medical supplies to underserved areas of Africa and beyond. These are just two examples of the many new and exciting applications of drones thanks to the advancements of autonomous flight. But as good as the technology is getting, nothing is ever perfect. Malfunctions, errors, mistakes will happen, and when they do, drones will crash. Drones are incredibly complex systems. Even this basic toy has a gyroscope, GPS, camera, battery, actuators, engines, and software, not to mention a subpar pilot. All of these components need to be working in sync with each other in order to keep the drone airborne and on mission. So when something goes wrong, you will end up looking through gigabytes of data for thousands of components in order to diagnose and fix a problem. That is where our design study begins. How can data visualization be applied to this problem in order to aid in post-drone flight analysis? But as researchers, how do you get started? Before we get into our design, I want to talk about the design process models. Traditional design study methodology would tell you that you start by reading academic literature. That works great if you're working in a well-explored domain such as blood glucose monitoring for diabetes patients. There will be many examples of techniques and applications specific to your problem to build upon and to compare against. However, if no application research exists, you're going to have to go more abstract. In our case, our problem does have clear ties to the subject of geospatial movement data, as well as trajectories. But it isn't always clear if research done in the context of airplane tracking or whale conservation will apply to our context of debugging and operating autonomous drones. And what about our potential users? Will they even find the methods of that research useful or usable? That's normally where domain expert interviews come in, but access to these experts is often limited. To help solve these two problems, we turn to grounded evaluation. Proposed by Petra Eisenberg, she says, grounded evaluation is a process that attempts to ensure the evaluation of information visualizations are situated within the context of their intended use. During this evaluation, you will go beyond reading academic literature and review and evaluate current tools, methods, and discussions within your target domain. This could include things like medical textbooks, commercial tools, even online discussion forums. Anything that contains relevant background to your domain is encouraged here. While this takes care of where we start, there's still a question of where do we go from here? There are many well-defined and popular design study models to choose from. Just because we're using grounded evaluation does not mean we can't draw from them. We aim to create a well-defined model for grounded evaluation by turning to existing design study methodology. We looked at both grounded evaluation and traditional approaches and attempted to connect the steps within each process. All of this research shares some degree of similarities. If we can identify where they are similar, we can use the knowledge they provide no matter what design model we are actually using. For example, while the first stage of grounded evaluation is well detailed in the paper, the rest is not as clear. If we follow the connections to the steps of other models, we can use the guidance that is written for those models on our own. After considering all of this, we decided that our model should have 4 steps: evaluation, task analysis, design, and implementation. But we can't forget that visualization design is an iterative process, and these 4 steps can repeat many times throughout development. We wanted our model to represent the nuanced changes that happen to these steps with every new iteration. A spiral is a natural metaphor to describe this. We can arrange our steps around a spiral where every new band represents a different phase of development. In our experience, development can be split into roughly 3 phases. early, middle, and late. In the early phase, you will be doing the initial evaluation and design, where you will review the domain as it exists and begin to create prototypes of what you think might work. This phase will largely be done with little to no user involvement. The middle phase is where you will recruit domain experts to validate and refine your early phase task analysis and visualization design. In the late stages, you will be deploying your tool to a broader target audience, gathering feedback from the larger audience and implementing smaller changes. With this model, we have a semi-cyclical process that slowly incorporates more and more users as it progresses. This will help ensure we are conducting research in the intended context and will hopefully lead to our goal of meeting user needs. But enough talk about methodology, and let's look at how we use this model to solve our autonomous drone post-flight analysis problem. We started by looking for users and communities that were flying and developing drones. This led us to PX4 Autopilot, an open-source drone flight system. PX4 and its umbrella project Drone Code are becoming ubiquitous in the world of drone development. It is a massive community spread out all over the world and in many different industries. Thanks to this open source community, we were able to get an in-depth look at this domain before we even spoke to anyone. We pored over the documentation, user-created visualization tools, and public forums to see what problems this community dealt with and how they went about solving them. We learned quickly how visualization of this data was important to this community. Existing tools used a mix of geospatial and temporal visualization techniques. This mainly took the form of static or animated trajectories on a map and line charts to display all the sensor data. After reviewing all this new information, we identified several areas where the cutting edge in visualization research could be used to improve upon existing tools. We also could create an initial task analysis and a list of design requirements. Using this information, we created our first prototype of the designs we believed could improve post-flight analysis. This prototype aimed to improve on the existing tools by linking the temporal and geospatial data together. This data is being recorded in time and space. We saw how seeing where data points occurred on the map could be just as important as seeing when they happened. We achieved this by encoding the data directly onto the trajectory with a color map, as well as some other uncommon encodings such as line width. To validate our task analysis and prototype, we reached out to the members of the PX4 community to conduct semi-structured interviews. We spoke to drone pilots and developers working with PX4, asking about the challenges they have and how they solve them now. In the second half of the interview, we showed them our prototype using real PX4 data. Our initial evaluation proved incredibly valuable here. Since we were already up to speed on much of the background of PX4, we could meet our experts on common ground and get straight to the novel discussion. Having our prototype ready gave us the opportunity to gauge user reception to new designs. More importantly, the prototype steered discussion with our experts towards the tasks they would use it to solve and what else it will need to solve them. If we were using a traditional development cycle, it is unlikely that we would have been already so far along by this point. From these interviews, we formulated 5 core tasks and decomposed them into 5 general design requirements. We then used what we learned from our prototype design and implemented a more complete version of our tool. Let me walk you through Data Comets and show you our design and its features. Data Comets uses 3 main views to show users their flight data: the map, the attribute panel, and the timeline. On the map, we can see the flight path and other geospatial attributes like waypoints of the flight. The flight path uses a color map to encode attributes from the flight. Altitude is currently being encoded, but we can switch the data by selecting a different attribute from the panel. Let's take a look at velocity. By encoding this data on the flight path, we can see details that would have been lost just using a line chart. Look how we can see the color of the path change, showing how the drone slows down and speeds up before, during, and after turns. The attribute tree is organized into 3 tabs. The Overview tab shows commonly viewed data. The All tab has the data from all of the drone systems organized by the system they came from. We can pin data we would like to compare together to see them alone in the Pin tab. Lastly, we can filter the data and also visualize the movement of the flight by interacting with the timeline. By brushing the selection window, we control what range of data is shown. This helps us filter large logs to only the sections of the flight we want to look at. Moving this window back and forth lets us replay the flight. Kinda looks like a comet, right? Now we can further validate our task and designs by deploying the tool and sharing it with the PX4 community. We created a forum post detailing how to access the tool online or run it locally. We also posted on the PX4 Slack channel to share our new tool. The initial reception was very positive, even receiving attention from some of the founders of PX4, and Data Comments was even added to the official project documentation as an analysis tool. We also conducted more interviews with experts and reviewed user feedback on the forum in order to further evaluate the tool and implement or plan changes. Since our launch back in August, Data Comments has seen 300 users launching more than 500 sessions, and the code has been downloaded hundreds of times. The grounded evaluation approach helped guide our research and allowed us to integrate cutting-edge visualization techniques with methods our users were already comfortable with. We achieved the goal of grounded evaluation as our research was firmly grounded in the context it would be used in, and we believe that we achieved our user goals as Data Comments has shown steady user adoption. We hope our experience in the spiral design process will further encourage the use of grounded evaluation by providing a clear guide for successfully conducting it. We also hope our design of Data Comments will guide future visualizations in the exciting domain of drones, as there is still much to be learned and visualized. Please see our full paper for more details and visit our tool at datacomments.com.
Well, bravo, and quite the video. I don't know, I see that you're wearing the same outfit and in the same place as where you made the video, but I don't see your assistant ready to answer questions. Is the seal over? Oh, good. I'm glad to see that the seal is not missing. So I'm looking in the chat. I don't see any current questions yet. You did get a seal of approval. Thank you, Naska. And I would ask one question, or a couple of questions I had. What is the sort of best current set of tools or group of things? How do people do this now? And if you were to have users try it both ways, what do you think their feedback would be? So maybe that's kind of what you got from your feedback from the PX4 community. But I'm wondering if there's a way to state what their without your tools kind of situation might be.
So there's a lot of user-created tools that are being used by the community right now. And from when I talked with the experts, they said that they would switch between 2 or 3 of them during analysis to really get the full picture. And what they would often do is they'd end up having to, check the initial data, then download everything, and then plot it manually in Python or Tableau or something like that. So what this tool is really trying to do is streamline that workflow by bringing all those tools together, while at the same time adding more cutting-edge features from visualization research.
Cool. Folks should feel free to pipe up with questions in the YouTube chat or in the Discord channel if you're in there. One other question that might not be for you, maybe this is a question for one of your citations, but I'll ask it anyway. The spiral design process that you described looks very similar to kind of the classic spiral software design process of prototyping and testing and evaluating and requirements analysis, sort of revision, and then repeating all of that. Is there a way you could say how it's different, or is it really the same thing in a more specific context?
I'd say it's more so the same thing in a specific context where you're applying visualization techniques, visualization domain study techniques to that whole process. But maybe it's a little more streamlined where those spirals are maybe made for larger companies working in large teams, and this is more tailored to a couple of researchers who are maybe working on their own initially.
And a seal, of course. Don't forget the seal.
Yes.
There's one question in the channel, on the YouTube channel, would it be possible to extend this tool to work the other way around, optimizing the flight path based on the data? In other words, do you think you could do real-time kinds of operations in any way with the basis of the tools that you have?
So real-time is definitely something I want to explore. There is software for PX4 that allows for real-time tracking. That's actually how these are flown most of the time. They hit autonomous mission, and then they have a real-time application that shows them the trajectory as it's flying, communicates back and forth. So being able to also look at the data as it comes in would be really cool instead of just the flight path.
And we have another question that came in, which is, while displaying all sensor data is a logical first approach, have you thought about more task-specific derived quality metrics that could be relevant for specific user tasks?
Yes, so in the prototype, we actually tried to do that a little bit. We sort of hand-picked the data, the attributes we were showing, and we'd add some statistical methods to them to help analysis. But in the first round of evaluations, the users didn't like that. They wanted to just see the raw sensor data like right away, because that's what they were used to looking at. Like they'll know what a bad line chart for a particular piece of hardware looks like, and they want to just see that right away.
Very interesting. Users always surprise you, don't they? Did they have any thoughts on any of those kind of things that might be derived that they would like? Is there anything that they thought you could do real time like that? Or not, not real time in terms of feedback, but real time in terms of display?
So there was one thing that was mentioned, and if I remember correctly, it has to do with the gyroscope inside these drones, where if something's wrong with that, the best way to debug it is to do some sort of Fourier transform analysis. And so we discussed also being able to see those data points and then adding the Fourier transform to them in the tool, instead of having to download the data and do that manually.
Very interesting. All right. Thank you, David and co-authors. And we will move on to our final talk today and paper. This one will be presented by Chao Ma, and the paper title is GT Map Lens, Interactive Lens for Geotext Data Browsing on Map. There are several co-authors, Shamal Al-Dahuki, Jing Yang,
Hello everyone, welcome
Xinyu
to the
Ye, Farah Kam, and MD Amaruzaman. So take away the video for our final paper.
Hello everyone, welcome to the presentation of our paper named GT Map Lens, Interactive Lens for Geotext Data Browsing on Map. Here is the outline for the presentation. First is background and what is GT Map Lens, why we designed GT Map Lens, GT Map Lens design, GT Map Lens performance, the case study, user study, limitations and future work, and finally, your opinions on GT Map Lens. This decade, many geotext data is collected. This type of data contains texts and themes with geolocation information, such as geotagged social media, crime reports, consumer reviews, and so on. They offer great opportunities for data-driven studies on many social and scientific fields. So, what is GT Map Lens? We designed GT Map Lens called Geotext Map Lens technology that allows users to effectively browse and study geotext data by interactive virtual lens on the map. Here, a lens moves on the map, and the semantic information from geotext tweets are displayed. The inside is the top keywords and the emerging keywords. The outside shows the categories. A tail can be shown for the moving trees. Several insights on the map shows the basic information of lens, word clouds, category names, and temporal distribution of the data. These insights can be hidden or shown by users. On the right is the anchor list. It shows the saved anchor of locations of interest. Users can click any anchor to open a detailed view for drill down study. On the bottom is a historical trace view. It displays a full trajectory of lens. It also shows the location of anchors in the city. Current popular visual analytics approaches for geotext data are visualizing hotspots and locations by searching keywords and selecting critical locations based on domain users' prior knowledge, then aggregating geotext data and visualizing aggregated semantics. But they do not support the following tasks very well. First, users do not have clear keywords or locations of interest in their mind, and users may want to navigate the geospace to find important geotext information. Second, users looking for discover surprising and useful aspects of data. Then, transition analysis may be important for geosemantics along paths. Also, cold spots could be identified since it could be important. Lens technology is a promising approach to address this gap. Virtual interactive lens provide focus plus context exploration in freely selected region of interest. We conducted a requirement analysis with a group of 10 professionals. They recommend the following features for the GTMap lens, which are lens browsing, lens semantics discovery, lens path control, location snapshot study, spatial comparison of multiple lens. Now, I would like to talk about the detailed design of GTMap lens. First is lens contents and semantics, which includes two parts, in-lens and out-lens. The contents in in-lens includes two columns of keywords, which are ranked by TF or TF-IDF weights for semantics. Lens keywords can be recommended by word embedding technology, and it could be filtered by users. The outlines is designed as circular bars and usually used for visualizing dynamic changing of categories. Lens context is a layer above map that shows contextual information to guide users moving the lens and to define preferred paths. For drawing a path, users can sketch a path on the map with a mouse, a touch pen, or hand drawing, or pick several control points. Then a lens moves automatically along the path. We use B-spline algorithm to insert points in the path to make the path move smoothly. Users also can control lens moving speed and path smoothness. Lens tracing shows the lens exploration history to preserve the area and the paths having been studied. This feature is important for users to compare the paths of peer lens and recall locations of saved anchors. For drill down study, GTMap lens allows users to save anchors to anchor list. They can click the saved anchor to trigger another panel to do detailed study. Users can also study the transition of topics in Topic Transition View. GTMap lens also allows users to apply multiple lens to do the content comparison and detailed study. Now, I would like to talk about the performance of GTMap lens. For quickly computing semantic information inside the moving lens region and speed up performance, we utilize a quad tree-based spatial indexing structure to store geotagged data points. More importantly, a new method is applied that pre-computes the cell semantics as top keywords, categories, and topics of the quad tree cells. For example, one cell stores a vector of keywords of the top n. Now n equals 100 keywords. Once the lens region is formed from a quad tree by a set of cells with different size, their semantic vectors are accumulated and used in visualization. We use two geotext datasets to do the case study. The first dataset is a tweets about Hurricane Sandy from October 22 to November 2, 2012, which caused severe damage in New York. A total more than 20,000 geotagged tweets in New York City are used. The second dataset has 18,000 geotagged consumer reviews from Yelp about POIs in Las Vegas, including hotels, restaurants, and entertainments from 2012 to 2018. I will show one case study that used the Hurricane Sandy tweets. To study the geotagged tweets about Hurricane Sandy in Manhattan, several high-density points are selected, based on the heat map showing the tweet density. A smooth path is then generated from these points. A lens can move automatically along the path, while users can control the moving speed easily. Here, the lens content shows top keywords on the left and the emerging keywords on the right. The lens contents help users find interesting topics. For example, an interesting keyword crane is identified here and saved this anchor. By typing a keyword flooded in keyword recommendation, the lens shows only similar keywords. Users then can push two more keywords to the list. At the end of the path, more interesting keywords water and river are shown, and then the last anchor is saved. These anchors can be opened in the detailed view. For example, the first anchor shows the twist about a partial crane collapsed from Sandy. The last anchor shows that the water on streets become a major topic close to the East River. Users can also refine the focus region for more detailed study. A parallel set view can be opened to show the trends of semantics among the 4 anchors. We evaluated GTMap length in 3 steps. First, we asked domain experts to evaluate its utility in their work. Second, we compared the new length functions with an existing tool. Finally, we performed a user interface satisfaction QURIs survey to evaluate the system interface and functions. At the first step, the domain experts provide good feedback and point out certain limitations of GTMap length. In comparative study, we compare GTMap length with bird length, which is one of the closest work to GTMap length. We compare them in following aspects including contents visualization, keyword display, path planning, length anchors, and comparison functions. The participants are 15 graduate students, 5 females, 10 males, 10 CS major with certain knowledge of visualization and interface. 5 were from domain fields in GRIs and its related subjects. Their ages range from 23 to 41. Then we train them to use both systems. After testing, they will evaluate both systems with 5-point Likert scale questions. Overall, the result shows the GTMap length performs better than bird length. The QURIs survey indicates the length path design and anchor functions received excellent rating that shows users like these features. For the system learning, the rating was good in average, indicates the system may need a training process at the beginning for general users. At the end, I would like to discuss the limitations and future work of GTMap length. In future, more functions and controls can be added to length. NLP and text data mining tools may be included. The tool is good at street or small region level studies. To be used on large geographical scales, it needs to be specifically revised for performance and visual presentation. The restricted scope of the work is length technology, which will be compared with other non-length tools in the future user study. Thank you so much for watching this presentation.
Great. Thank you, Chama, for recording that and sharing it with us. If you can unmute yourself, I will try to relay some questions from the audience. The first one is, have you tried to apply your approach to more complex data, for example, browsing through large, like semi-structured data sets in XML?
Actually, our data should be, the raw data is come with a CSV file. And the data have most of the important semantic information, and we should pre-process the data first. And since we use a quad tree structure to store the keywords vectors, so basically we need to process the data first. Yeah.
One question that I had myself was, I thought your bird lens comparison was great.
Yeah.
Now there's 2 of me up on the screen. I was wondering if you could share a little bit about what the improved performance things were. You had some graphs, but they were kind of small and hard to read. Maybe you could give us a bit more detail on that, and maybe on some of the Likert scale data that might be of interest more generally. What lessons would other designers take away from your work to understand how significant it is?
Okay. Actually, for the Birdlands used actually they didn't address the exactly text information. Actually, they used the categories. So the hard part the hard part of to address this is because we need to address the topics and the ranked keywords and also we use some word embedding techniques to attract the important information from the text. But Borderlands they use the just the categories, so that's simple. That's more simple. Simpler than track the information from the text itself, and and for the five record study, we actually use the standard five record. So we ask, this is kind of the user study. So we studied by just ask them to fill out the from 0 to 5 because it's 5 points record. So what's their satisfaction on the 5 important the part, such as the visualization, the lens path, the lens browsing, and etc. This kind of functions. If they compare our lens, GTMap lens with Borderlands, so they have their they just rate the grade their the comparative study to, and they have the more higher scores on the path length and on the length on the path and the path control, because they think this function is really useful and important.
Okay. Terrific. I think no more questions in the channel right now, so I think we will wrap this session up a little bit early. And Chao, it looks like your voice. Oh, maybe I'm just looking at the recording. Yes, I think we'll wrap up the session now. And thank you all for attending, and thanks to all the speakers for preparing and their presentations and bringing them here and sharing their answering of questions. And hope everybody enjoys the rest of their day and conference. Thank you.